right? So let's start here. So as I said, we're going to focus on physics of the atom. We'll do a quick little summary. It won't take us long at all, right? Everything here is in a summary, right? Everything here is in a summary. I should be shall start again now, right? All right. Everything here is in a summary. So we'll do a couple of questions, probably start with a few multiple choice and then work our way into a few paper tools. All right. Or the other way around. All right. So first thing first, the first thing that they did, or we have to know about in physics of the atom, is how they came up with the model of the atom. Right. The first thing is seen as a definition for radioactivity. Right, the emission of ionizing radiation of particles caused by the spontaneous disintegration of an atomic nuclei, right? So something to point out there is radioactivity is very spontaneous event. Anyway, we'll come back to radioactivity, but the first thing I wanted to look at is the first thing we have to remember is the Geiger-Marsden experiment, right? What they did here at the Rutherford's lab is that they shot alpha particles at a sheet of cold foil, right? And alpha particles, in case you don't remember, alpha particles are helium atoms, right? So it's a helium atom, charge +2, mass number 4, atomic number 2, okay? So alpha particle going to the cold foil, and a few things happened, right? The first thing that happened is that most of them went straight through. What was the conclusion? Most of the alpha particles went straight through. So the first conclusion was that the atom mainly had empty space. I remember that? Yeah. A few of them were deflected, which meant that the atom had a small positive core, and an even smaller amount of was reflected. Right. So you'll recognize here, most of them went straight through, or some of them were deflected slightly, and some of them came back at you, which meant that they were reflected, right? So the third conclusion was that core that was small, it was also solid. And from there, they came up with the model of the atom that we know, right? The model of the atom that we know, I didn't draw it here, sorry. I'll fix that in the new crash course thing, right? We know that the atom has a small dense core called the what? Michelle, what is called a small dense core? What is called this here again? It's called the nucleus, right? And inside the nucleus, you have your charge, the positively charged particle called the proton, and you have your neutral called the neutron. And around it is the what? Let's say, around it is the shells with the electrons in it. Okay? So that's basically the model of the atom that we will use, right? That's the model of the atom that we're going to use. Right? Mainly empty space, has a small positive core, has a shell with electrons on it, right? Here is your shell with electrons. Right? As a quick review, see if we could draw this now. I'll help with us now. See if we could draw, right, let's not go too big. See if we could draw sodium. Sodium has a mass number of 23 and an atomic number of 11. Actually, let me help you out, right? If you could do it, go right ahead. All right, so what I want you to remember is this, right? It's not on this side. Look at it. Oh, wait, no, I'm missing it. Oh, gosh. Anyway, good. So that's something to fix in this handout. I'll fix it for you. Right, so we need to remember that if we have 2311 sodium, that 23 is your mass number. Okay, that 23 is your mass number, which is your protons plus your neutrons. And the 11 is your what? Your 11 is your atomic number, which is your proton number. Remember, protons equal to electrons if this value here is 0. Right? If you don't see anything, it means it's neutral. So in our example here, how many protons it have? Shavish, how many protons this have here? Now, that's the atomic. I mean, that's the mass number. How much you think? How much you think the mass number is? Sorry, the atomic number is. The atomic is 11, right? Which is the same as the number of protons. So protons is 11, electrons is what? Vishal? Huh? No, the protons equal to electrons here. Right? Protons is 11. And neutrons is what side? Take your mass number and minus your atomic number. Yeah. Which is protons plus the neutrons. And the electrons always equal to the protons. Right? How we drawing this? You have to remember the first shell could only hold 2. We have 11 in all to get, right? The first shell could hold 2. The second shell could hold 8. So that'll be 2 plus 8, that's 10. We have one more electron here to make it 11. So you put it in the third shell. So you have to be able to draw it. You have 3 shells. 1, 2, 3. The first shell could hold 2 electrons. Second shell holds 8 electrons. That's 10. And we have one more. All right. That's the way you draw an atom. Right. And in physics, you have to tell them that you have a nucleus here with 11 protons and 12 neutrons. Right, make a note here because I do have an example, right? Okay, so that is how you draw an atom, right? Next thing, we want to take a look at radioactivity. We have 3 types of radioactivity, right? 3 types of radiation, sorry, an alpha particle, a beta particle, gamma ray. Alpha particle is a helium atom, a beta particle is an electron, and gamma is a ray. Okay, those are your 3 types, right? We need to remember a few things about each one of them. Oh, by the way, if you have a reaction, right? Let's say you have 21248, I'm just making up something, right? Pa, and it loses our alpha particle. What you have to remember is that the new particle, right? The new particle will have a mass number. Plug in now. I got a laptop on. Log in in the meantime. Right? Log in. Right, the new particle will have a mass number that is 4 less than 212, so you're -4, and then atomic number 2 less 48, right? So basically, if you add up all your products, if you add up your mass numbers here, right? If you add up your mass numbers, it's supposed to be equal to 212. If you add up your atomic numbers, it's supposed to be equal to 48. 548. 548132. Now, okay, so that's your radioactivity there. Right, same thing with beta and gamma. What would happen if a particle loses a gamma ray? Anybody online could answer that? What would happen if the particle loses a gamma ray? Right. There will be no change in the particle, it will just have less energy. Right? It will be the same particle, but less energy. Okay. Here you have some things, but look here in the meantime before I log out. Right? Here you have some things with alpha, beta, and gamma. Alpha is stopped by paper, gamma is stopped by lead, that should be PB, yeah? And beta is stopped by aluminum. Alpha could travel a few centimeters in air, beta could travel a few meters in air, and gamma could travel a few kilometers in air. Right? Let's see if we remember how they behave in an electric field and a magnetic field. If I could go back to in the summary, just go back in the group and you see the summaries there. The second summary, the first one I sent you actually better than this one. All right. So alpha particle is positively charged, right? So where would it go? It will go towards the positive. Yeah, positive attracted to positive. Very good. We're going on with all your generation, man. Real shaking your head and thing to what you know. Right? Positive is attracted to the negative. Right? What about beta? Beta is negatively charged, so it's attracted where? Negative? No. So the negative will go where? Towards the positive. Nice, Samira, but we have a slight problem. What's the problem? We have a slight problem. I can't just draw it exactly like the alpha. Why? Have a reason why. Why? Jaden, tell them that. Why the alpha does go longer than the beta? So yes, the part's shorter, but I want to know why. Forget right on. Right? Ranju said because the alpha heavier. Correct. Remember the alpha is 4.2 and the beta is 0 - 1. So the beta light. So it's easier to pull it out of the field, right? And gamma going where? You'll get this one right, Vishal. Very good, Vishal. Very good, Vishal. You know what? Very good. Yeah, get that one right. No, she was saying that before. All right, so good. So the beta going to positive, alpha going there. What about a magnetic field now? That was an electric field on top there, right? What about a magnetic field? Basically the same thing, right? Alpha going up, gamma going straight through, beta going down. Right? Top is the electric field. Bottom is the magnetic field. All right, just catch it now, not in the summary. Write it again. You have to look back. I don't want you to look back. Write it again as it is. Some revision you're doing here. There's revision, so write it down. All right, so that's the way the alpha, beta, and gamma behave. Let's take a look at something else. Right, next thing, half-life. Oh, wait. All right, done? Okay, good. So that's the way the alpha behave in half-life. You gotta remember half-life. Time it takes for half of the present element in K, right? Right. So the formula to find the fraction left is 1 on 2 to the power n. So a quick example, if you have something with a half-life, let's say I gave you a half-life of 2 days. Quick example, right? If something starts at a whole or the 0 day, this is days, right? Then after 2 days, it will reach half of the original present, sorry. The original right now, present right now is 1. Half of 1 is a half, right? After 2 more days, how much it will be? It will be half of a half, which is 1/4. After 2 more days, that's 6 days. Right? Half of you, you're looking at anything? After 3 half-lives, here's 1 half-life, here's 2, here's 3. After 3 half-lives, it will be 1 over 2 to the 3 or 1/8. As a quick little guess, after 5 half-lives, what fraction it will be? Vishal? After 5 half-lives, what fraction will be left? Yeah. What's the formula? 1 over what? 2 to the power 9. So that'll be 2 to the power 5, right? So that's 1 over 32, right? So if 1 over 32 is the fraction left, how much decayed, Jaden? If 1 and 32 remaining, how much decayed? How you find that? You had a minus 1 and 32 from 1. Right? So that'll be 31 and 32. If you have a cake, and the cake had 8 slices, right? And 1 slice remain. How much you eat out already? Cake had 8 slices. And you're left with 1. How much you eat? 7/8, right? So yeah, that's minus 1 minus 1/8. Same thing here, right? If 1 and 32 remaining, then how much left? 1 minus 1 and 32. Okay with that? So you have to pay attention to what they're asking in Chivish. If they're asking you what left, then you give them these values. If they're asking what gone, minus 1 from it. All right? So that there, so there's the formula where to learn 1 on 2 to the power n. So write this down, right? Because we're going to be using this. Right? Make sure you have that formula because we're going to use that. Right? One thing I want to point out, if you look at the graph above, right? Suppose I ask you to find the half-life from a graph. you have to always remember you have to take 3 readings. And then from those 3 readings, you find the average. Okay? So your first reading is here, that's 0. Then you find half of that, which is this. And then you come down here and you take your reading. That's half-life number 1. Right? That's half-life number 1. Okay? Then you do it again. You find half of this, which is this. Come across here, take your second half-life reading. But watch this here. Notice when you get this reading, Shavish, you're not subtracting from 0. You're subtracting from the values that was double it, right? So for example, if here's 100, here's 50, here will be 25, here will be 12.5, right? So if you're reading up for 25, it come here, come down here. Please remember that you're using as your original value, the value of 50. And you're subtracting the value here and the value here. That will give you a half-life. So you have 1 half-life, 2 half-life, 3 half-lives. Then you add it up, divide by 3. Okay, please, when you read this value of, don't subtract it from 0. You're subtracting that value of from the value just before it, right? No, not the first one. Look at it here. The first one is here to here. Your first half-life is 0. The first half of your first value. Yeah. And then here, you subtract this value from this value. I don't have numbers, right? But if I had numbers, it might have been like something like this, right? 2, 4, 6. So your first half-life will be between 0 and 2. 2 seconds, right? Your second half-life will be between 4 and 2. 2 again. Your third will be between 6 and 4. 2 again. Your value shouldn't be double and triple. If that happens, you do something wrong, right? It should be real close to the first value. Then you add it up and divide by 3. So if you see this in your past papers, that you have to find 3 values, right? It came up a few times and I gave it like 10 marks with it, right? Yeah, so when you plot the graph, you have to just take 3 readings or plenty marks. And last thing you want to look at is Einstein's energy mass relationship, right? E is equal to delta mc squared. Delta m is, so if I give you a reactance, energy mass relationship. Energy mass relationship. Right? So if I give you reactance, that triangle means change. Right? Change in mass. But now tell you change in mass. You be listening, right? Right? Change in mass. So you find the mass of the reactants, you find the mass of the products, and you minus them. Huh? Oh, it's 548143. I remember the password. Okay, so to find the change in mass, Jaden, all we're doing is whatever the reactants are, add up the mass. Whatever the products are, add up the mass, and then subtract them. Okay, that's the hardest thing, right? Please remember this must be in kilograms, right? And when you find the change in mass, multiply by the speed of light squared. That value is the speed of light squared. Okay, so we're gonna try a few. Let's start with some multiple choice. It might have 1 or 2 small things in multiple. Might have a few things I need to remember from before, right? But let me check it out. Let's do a 2018 now. I'll do a little multiple choice here. Let's see. Right, let's start from 54. Yeah, 54. I'll see in that. Too small? All right. Do these 4 then. But sorry, 3. Do those 3 and then message your answers. Oh yeah, 54, 55, 58. Finish it. 2018. Samira finish already. Samira is done and waiting on Jira. $54, $55, $58. Hey, let's play in the boy. Vishal, I don't know what. Well, let's go and sit on my Vishal. Right, first one. Jaden, which one there is half-life? The first one that we done. No. Give me quick. Which one there sounds like the best answer? A, B, C, or D? C? Half the time it takes for the radioactive nucleus to decay. All right, let me see. Half the lifetime now. D out for sure. Dog out for sure. Let's check out point. The time it takes for a radioactive sample to decay. I like that. B out for sure. Right? Always remember, we should always have 2 good and 2 bad answers, right? A, the time it takes for half a radioactive sample, radioactive atoms in a sample to decay. Yeah, I like it. It's not half the time. It's the time taken for half of the radioactive elements to decay. It's not half the time, right? So the answer is apple. 55, Shavish. Oh yeah, Albert Einstein. You sure? Why I say that? Huh? All right, Daddy energy mass leadership. Nice. 58, Vishal. You say? You read it? All right. Which of the following statements about radioactive decay are correct? It's a random process. I'll take that. Yeah? A random? Jaden? All right. Jaden say yeah. It is dependent on conditions X2. It is dependent on conditions. You sure? All right. Let me check out 3. I don't think it depends on anything. It is due to the charges in the nuclei of the atom. Oh wait, just now. Which are the above are correct? I wonder. No, that's not to read it over. I'm just read it over for what? Yeah. I'm not too sure you're it's a random process, 1 in for sure. It's dependent. It shouldn't be dependent. It's due to changes in the nuclei. All right. Yes. It is due to changes in the nuclei of the atoms. Yeah. 1 and 3. 1 and 3. Boys. Right? It's not dependent on anything. So it can't be 2. Right? So 1 and 3. Right? Let me scroll down again. Do 56 and 57, 59. Oh, wait. Let's do 55, 56, 57. Do those 2 there for me. to those two? Then 56 is yours, right? 57 is sorry. Oh yes. Very well, right? Timber, you're going to camp somewhere. Yeah, by a beach house. It's not considered camp, but I just go and lie down in the grass. Yeah, I'll be now. Right, let's go 56. Jaden, what do you think? Gamma, I'll take that. C, 56 is C. Nice. Dimitri, third is wrong. It's had to be, I say C. The correct third. 57. Right, 57. The nuclei 234TH contains contains what? Yeah, so here, this is yours. Huh? So you say E, 90 protons, 234 neutrons. Are correct? Shavish? You thought it would have been C. Huh? C something good? So you say all? All right, but you sure you're right. Right, so you say all four. So yeah, let's move on. Right, the answer is C, right? No, but that one not it. You didn't say A, B, C, or I say C. You say all. No, I said right, so the answer is C. 90 protons, 144 neutrons. How we got the neutrons again? 234 minus 90. Mass number minus. I can't believe we get that wrong, sir. Sorry, because they get that wrong. Let's, in fact, no, I want to pick somebody online here. 59. Let us pick, give Dimitri one already. Elizabeth, what do you think 59 is? Will you message me? Elizabeth, what you think about number 59? Come to start when? Like, what is the church camp? Church camp is what, from today or tomorrow? Tomorrow. That'll be real good, right? I should be better camp better than carnival for that, yes, I know. Should be real good. I went one at a time up picture rights. What's it? Bad. Bad. Right, where Elizabeth? Did I get? Oh yes, Elizabeth said D. Let us see if D is correct. Right, D is correct. What did you say, Dimitri? If I have class Monday, Michael, no class Monday and Tuesday. I might just do some recordings and post it up. Wednesday, yeah. Wednesday holiday? But Monday and Tuesday is not even my holiday. It's just so what that mean? What are you doing Monday and Tuesday? Just make sure you're sober for Wednesday. All right, yeah. Let's go again. 48, 49, 50, 60. I want all the answers for this one. Everybody. Which one is correct? Those who online message. Where Halls? Halls, are you there? Work out 60, please. Work out 60. Let's see what you get. One answer, Dimitri. Right, did Dimitri submit his already? Well, he submit 3 answers. Ranju, Shivani, good. All the answers coming in, all, yeah? Huh? Run through all the small things can trick you, right? Because at the time and the place and we feel it. We feel it. We feel it. All right, good. Let's say I've been waiting on my answer. Where again? A. So I waiting on that. A correct? When you lose a beta, the atomic number, the mass number is changed. So why do I go to no small bit? Right? Right. So once you lose beta, the mass numbers have to stay the same. So that's out, that's out. Okay. What would happen if you lose a alpha? Shivish, what would happen to the mass number? It jumps by how much? The mass number jumps by how much? Or we do one like this, Shivish. How much in mass number? What's the mass number of alpha? What's the mass number for alpha? 4, right? Lock it off, my right? So the mass number will drop by 4. So the only one that did that is C. Right? So you have to remember those things, right? Mass number drop by 4, atomic number drop by 2. So the answer is C, not E. All right. All right, good. Let's squeeze in one more. Anybody get all right? Oh yeah, some people did get no. They didn't get all right. I will squeeze in one more now. I'm just trying to see if I could avoid repeats. I can't really avoid repeats, right? But let's try 2021 real fast. If we get all right here, I'm finishing class early. Nah. Start here, 55. 55. This man really messaging people, boy. You messaging. Tell them your lessons now. Tell them message at 5 o'clock. Number 5, message answers. Sorry, 55 message answers. Is that like chemistry, right? Right? That was like chemistry. You're just counting backwards. You're counting backwards. If F is 9, O is how much? Right. So B is how much? Yeah. 5, yeah. So you're just going backwards. Yeah. We didn't never see a period. Yeah, it just going in order. It just going in order of atomic number. All right. I think nobody asked that. 55 is A. 55 is A, right? 55 is A. 56. Is that a repeat? No. 57 is a repeat. I'm going to say only is 57. 56, and I want you to tell me what was the letter for 57. Not the answer, not the actual particle. Tell me about A, B, C, or D. Work out 56 first though. What's 56? Number of neutrons. Work it out fast. Shavish, 56 is yours. Oh yeah. Do that mentally in your head, my boy. Are you anything? Huh? LB? That's not whoosh. Right, so it's 222 minus 86, and I get 136, which is C. Okay, you get that? All right. Let me see how good all the memory is now. We know the answer, right? Yes, Dimitri. I see what you did, Dimitri. Rob I entered. Who's Rob I? Somebody's Rob I. Right, yeah. Help me out here now. Yeah, we know the answer is what? Gamma. But what do you think? Anybody remember what it was? We did this in the last one. 57 was what? A, B, C, or D? Yes. It was a C? Let me see. Nah, they don't even change up the they don't even change it up sometimes. Oh, Robert Bernard. Okay. Robert. Robert. All right, so the answer was C, yes. All right, let's go 58. Work out 58. Everybody, message your answers. Smile, yeah. Let's make sure that door look. 58, work it out.
Because I have one jacket. No. Here, what do you have on a jacket out of New York, right?
Right? What you all got here? Right, so what going in there? Remember, you recognize that what stay the same? The mass number stay the same, right? So what particle going in there, Jaden? B, yep, 0 minus 1e. 0 minus 1e, right? Right, so it's a beta decay, 0 minus 1. 59, real easy. Put this covered radium. Put this covered radium. With a lady. I'll never hear the story about a lady.
You know, I think that should be around.
The answer is A, right? Mercury.
Mercury.
A. Right, was Mercury, right? Well, I heard the story about the first female physicist to win a Nobel Prize. It was a number 60. Yeah, she still didn't get credit for it. Last one with half-life. Last one is 60, right? And when we finish, we'll do a calculation with Einstein's energy mass relationship, right? And we can wrap up there. What is it? Yeah, should we work it out? Why? Half-life. Try it out, tell us how. I'll tell you that's how. How much half-life would have happened for it to reach 1/8? Right? Right, so here, 2 to what power give you 8? 3, right? Yeah, Jaden? 2 to what power give you 8? 3. So it means that to reach 1/8, it took 3 half-lives. How long is 1 half-life? 20 days, right? So how long is 3 half-lives? 60, right? So the answer is boy. How many days will it take for a given sample to reach 1/8? Right? The answer is 60 days. All right, last thing I want to do with you, I want to do a radioactivity. I mean, Einstein's energy mass relationship, right? Not really prom. There are plenty of people now. But we have graduation on there. I might try something, but if I get a nice space, I could do it. Right, let's just try one here. Oh no, what's the matter there? Right, so let's give this a try. This is an old year, right? This is 2005, I think. (2005). Try it, please. Take your time. I'll give you a few minutes here. Real old school. Some of the questions I'll be giving you in crash course, I think is 1998 and thing. Because we do, if you all check your books, we do almost everything, right? Yeah, it'll be a little more challenging. Yeah, what's Mari's up now, right? After you talk, right? Try this summer, please. The whole thing, everything. 2005. Right, I'll give you a few minutes. Let's stick anywhere, let's move on, right? I know we didn't go through all the rules for medicine and agriculture and thing, but try and do it out. Write the equation and work it out. Yeah. I mean, how was it? Better? All right, let's try and get this right, okay? Take your time and write all these things, right? What is E and what is D, write through all of this. Right, let's run through the first few parts. Let's run through the first few parts. A is what? They want to explain the meaning of E and Z and write an equation relating A, Z, and N. A is the what? A? No. A is the? What's A? The one on top, the bigger one. Now, A is the mass number or nuclear number. Z is the what? Right, Z is the atomic or proton number. And what's the formula relating all of them? Shivish. What's the formula relating A, Z, and N? N is equal to? So the mass number plus Z, give N. Try to remember. A minus Z, right? Or you could say A is equal to Z plus N. Okay? What's an isotope? Write it down, boy. What's an isotope? Copy it down. And tell me what's an isotope? What's a radioisotope? Z. Yeah. Huh? Same atomic number, but different. Well, yeah, mass number, yeah. Right, so isotope, same atomic number with different mass number. Same, so same Z, different E, right? Same atomic number, different mass number. So basically different neutron number. Shouldn't write it down. I just called out 4 and then write it down. All right, next one, radioisotope. Right, I don't think you have this one in the summary, right? So write this one down. A radioisotope is an unstable form. A radioisotope is an unstable form. Unstable form of a radio. Sorry, it's an unstable form of an element. Unstable, underline unstable. Same atomic number, different mass number. That's 5 times that I call it out. Right? A radioisotope is an unstable form of an element. Six times that I say. That's not how I start over radioisotope. So you ready to write radioisotope now? Right, the radioisotope is an unstable form of an element that releases energy. / radiation. It's really radiation and releasing, right? That releases radiation. That releases radiation to become stable. Right? What are 2 properties of radioisotopes that make them useful in medicine and agriculture? Anybody can help me online? What are 2 properties of radioisotopes which contribute to their usefulness in medicine and agriculture? Why it is radioisotopes useful in medicine? Right, no. Yes, it's used in treating cancer, but why? Why it's useful in treating cancer? Because it radiates Ishana, what is that? Ishana. Pacemakers for heart. Right, no. You're listing the things that they could use them for in medicine. Question asks why. 2 properties. Why we could use them. Okay, so why we use them for treating cancer? What does gamma radiation do to cancer? Kills the cells, right? Right. So one of the properties is radiation. Radioisotopes could penetrate muscle and bone and kill radioactive cells. Well, that's 2 actually. They have a high penetrating power. and they could kill cells. Well, actually, they could kill both healthy and cancerous cells. Yeah. Treatment probably didn't work. Right, so they have high penetrating power. And second thing is that they could kill cancerous cells and useful cells. Right? Right, and next thing is that they could beeping on me. Yeah, that's all. Right, and the second thing is the short half-life. Right, this a next property of radioisotopes is some of them have a short half-life. So when they enter a body, they can come back out in a short period of time because they would have died, right? High penetrating power is one of the main uses, and the second use is the short half-lives. So they decay quickly. Gina, you didn't write it down. The second one, short half-lives. Short half-lives. Yeah, but write it down. That's the two main uses of radioisotopes, or the two main properties. Right, so the question didn't ask it to list it out, right? They just want the properties that allow them to be used in medicine and culture. All right, move on to C. Move on to C. Determine the distribution of electrons and draw a label diagram of silicon. Go ahead, I'll show you this one already. Go fold your arms, Sivish. Do it. I'll show you one of this already. How much electrons does this have, Shivish? Huh? Read it and see. You read it and see. And tell me what we answer already. Well, how do we see exactly? So you answer it for yourself. Right? What is the number of electrons in that particle? 28 Si14. What's the number of electrons? Electrons, huh? Huh? That's electrons. And what did I say about the protons? Right. Right, so it's 14, but they want the distribution, right? So they want to write it like this. 14 means how much in the first shell? 2. Second shell is how much? Electrons is 14, right? 8 in the second shell, how much in the last shell? 4. Right? And then you'll draw it from up. Okay, draw it fast. And then let's move on to the calculation, right? We'll do the calculation together. 3 shells here. Make sure you write what happens in the protons in the nucleus, right? Yeah, you have to write that one. Right, move on to the next one now. So you should have finished drawing by now. So you have your nucleus and you have your 3 shells, right? Sorry. Right, 4 on the outside, right? And tell them that you have a nucleus here. Nucleus with 14 protons and how much neutrons? 14 as well, right? All right, let's take a look at right, let's take a look at the last part now. So develop a nuclear equation representing the fusion of 2 deuterium nuclei to form a helium. All right, so let's see if we could do that fusion reaction. Okay, so watch here. 2 1 H plus what? Plus what, Hishal? No, read part D again. Yeah, we're trying to develop the reaction. We're trying to create a reaction. 2 reactants giving you a product. What are the 2 reactants? Sorry? That's the product. Right? What's the next reactant? Should we up to now you look at the question? We read it and see. Right? What they produce in there, Shavish? What is being produced? What is being formed? Huh? No, what particle is being formed? 4,2-H3, right? 4,2-HE. What form in them, Shavish? Right, that's the product. Yeah. What form in 4,2-HE? Shavish. Read the first line again. 2, right? So I have to write 2 of those particles, right? 2H1, 2H1. Add it up there. They're working out. Check the mass numbers on the left and the mass number on the right. Check the atomic number on the left and atomic number on the right. Adding up. Okay, nice. So what's here now? What's the formula? They want us to find what? Take a read of the whole thing, tell me what they're asking to find. Take a read of the whole question, tell me what they're asking you to find. That's not what we should looking up there. Yeah. Go ahead. What they're asking you to find, Michelle? So what's the formula we're going to use? E is equal to what? Delta M C squared, right? How you find delta M again? How you find delta M, Jaden? Add up the mass of the reactants and minus the mass of the. So mass of the reactants minus mass of the products. Right? What's the mass of the reactants? You all seen it here? 2.014102 plus 2.014102, and you're minusing a helium, right? 4.00263. How much is that? How much is that? Gotta be exact, no rounding up. Absolutely no rounding up. What's the third number? 4.00263. Anybody online? How much you all got? Remember, no rounding off here, right? What you guys, Shana? What you guys should be? 0.02. Right. 0.02557. 4. Right. We have a slight problem here. This mass is in U. We cannot use U. We have to convert to what? Kilograms. Right? And the way to convert it is 1 point, you multiply by 1.67 by 10 to the minus 27. How much is that? No rounding off, eh? 1.67 by 10 to the minus 27. Huh? 4.00263. How about here? We're waiting on. Huh?
Yeah, 4.2, 4.27.
Wait. 4.2. Yeah. That can be there. Look again. All right. Anybody get our online again? 29. Kind of rough from up there, boy. Put 28, put 29. Anybody else got that? 4.270858. Anybody else get that online? Check it back from again now. Some people not saying yes. 10 to the by, that's 27. Yeah. Yeah, online. How much all I got? Oh no, what happened? Final answer, yeah. Check us at kilograms. Work it out from again and see now. Any answers online again there? I'm not seeing anybody messaging. Well, I get that. You work it over.
Yes, we can.
All right, well, let's use that. Let's use that, right? So NG is what? E is equal to delta MC squared. So that's 4.270858 by 10 to the minus 29. You're multiplying that by the speed of light squared. So that's 3 by 10 to the 8 squared. Work it out for me. 3 by 10 to the 8 squared. Work it out for me. Online message your answer, please. I would not should we try to work it out. Something wrong. Nobody online responded. How much will I get? 3.4, your squared.
Square.
Some people get a different value, 4.245284 by 10 to the minus 29. I don't have my calculator. Samira, what you got for your delta M value?
Yeah, I had gotten the same thing.
Oh, you get the same thing? All right. So multiply it out. What you got for the last value? Why am I not seeing Dimitri? Dimitri, I know you're messaging, man. I'm not seeing it again. I just see you message and disappear. All right. So I see in 3 point. Yeah, call out your some of that 3 point. 22 by 10 to the minus 12. And that answer is in what? Energy is in what? Energy is in joules, right? When you reach here, feel free to round off, right? 3.84 by 10 to the minus 12. All right. So that's your